Okay, so today we are looking at day 4, and I'm trying to keep pace with covering the material that's on the assignment. Now, I apologize for the assignment that you have in the back of your notes for this because we broke them up differently, and this is an old notes that somebody copied off and got done. So it's kind of a bummer about that. But I want you to look at a few things today. And I broke this down earlier, and maybe perhaps I should just take this here and here, and I will talk about it this way. Even in oddness, okay? Even symmetries. If a function has even symmetry, when we did this in geometry, you reflected things could be reflected across the y-axis. You had the y-axis symmetry is an even function because whatever's on the right side of the y-axis is on the left side of the y-axis. That's an even function symmetry. So f of x equals x squared is a great example of an even function. Okay, and in an even function, what it is whenever I put in the opposite of x, I get out f of x. There is no sign change when I put in the opposite of an x value. So if I put in 2, if I have 2 and I put in -2, there's no change between -2 and 2. And that makes sense for my y-axis, my y values, or my range values coming out. In an odd function, okay? An odd function is defined this way. The opposite of x is put into f of x. And what happens is that all the signs inside that function get changed, okay? Not just 1, not just 2, not just, well, you know, that constant didn't change. All of the signs have to change in the function, okay, for it to be an odd function. Okay, so as you're going through, the most typical one that I have here is a cubic. Okay, because everything in that first quadrant is everything in the third quadrant. Now, here's the thing. When you went through geometry, you learned something about point symmetry. Okay, and you're like, yeah, you know, you had that rotational symmetry and you had line symmetry, but then we had point symmetry. And point symmetry was symmetry that you had, rotational symmetry that you had that was exactly 180 degrees. Well, exactly 180 degrees about the origin of the XY coordinate plane. If you look at what's happening here, if I can take my function that I have, and maybe perhaps hopefully it'll let me do this, and I can rotate my function 180 degrees. Oh, I brought it back to the blue, but it will have point symmetry. So point symmetry is a 180 degree rotation about the y-axis. So you can identify functions that have even symmetry because the y-axis is its mirror line, or you can identify a function as odd symmetry because if you rotate the function around the axis, the origin, around the origin itself 180 degrees, it should come back to itself. Now that's pictorially what even and odd mean. If I'm going to do it algebraically, for an even function, when I put in the opposite of x inside the function, I should have no sign change of the function, okay? It should be the same value. And it kind of makes sense, otherwise I wouldn't have my parabola look the way it does. When I do an odd function, when I put in the opposite of x, I should have all the signs change. And up here, that's what I've got, no sign change. When I'm talking even, all signs change when I'm talking odd, okay, algebraically. Now, my example for checking, okay, I'm looking at this function. Right now, visually, it's looking like I have my y-axis as my axis of symmetry, correct? So now what I want you to know is that, okay, I can probably identify a function quite quickly, or at least surmise that maybe that particular function could be even or odd. I should be able to check it algebraically to prove it to myself. And how I do that, I put in the opposite of x, okay? Now, if it was going to be even, this would be the even check, okay? If it were going to be odd, this is my odd check. Either way, I place in the opposite of x into the function to see what is the result, okay? So let's check out the function itself. I've got f of x, and actually I've got this prepped here on this one, I hope. I've got f of x, x squared minus 3, okay? Now, let's reason through this. If I place in the opposite of x and square it, will it change any signs? If I put in the opposite of x and square it, did I change anything? It's the same function, right? Yet I put in the opposite and it come out. So I know this function's an even function because of the result, and that's an algebraic check. Okay? Yeah. Yeah, but now keep in mind what I put into the function. I put in the opposite of x, and I can only put that in where I have the variable. Okay, so since 3 is a constant, that's also one of those indicators of let me know that it won't turn into an odd function. Does that make sense? Because that sign won't change because it has no variable to make that change when I do the check. Okay, are there other questions with that evenness and oddness in function? Now, you know, the biggest thing about even and odd functions is when we get the sine and cosine. We will treat them differently because one's even and one's odd. And based on their evenness and oddness, it makes our manipulation of the function when we need to like squeeze it, stretch it, rotate it around the axis, it will actually make that job easier because of evenness and oddness in their function. But I won't go into that any more than just that one statement. So we'll talk about evenness and oddness in chapter 4 and chapter 5. Okay, now, the next one, B. I got a lot of stuff in there. I want to make sure you guys get it, so I'm going to group it. I want you to think about it and look it over for yourselves. So although, you know, everybody's there, I'll bring you back. I want you guys to try it. It's your turn. We just talked about evenness and oddness. What do you have to do to check if something's even or odd? First thing, place the opposite of x in as the value x. Okay, go ahead and make the check. Take the original function. Okay, be very deliberate about putting the opposite of x in inside parentheses and square it. Put the opposite of x in for both sets of variables. Right now you should have an inkling that there is going to be a sign that doesn't change. Okay. As we're going, I put in my opposite of x. Okay, are you okay with this algebraic check? This is like, you know, if someone says, well, prove that to me. The facts are, if you're going to look at an even function, f, when you put the opposite of x in to the f of x, you should get the same value as f of x. When you put in the, when you're looking at odd, if you put in the opposite of x into f of x, you should get the opposite of whatever f of x is. That means all the signs will change. If a little bit of both changes, that means the function's neither, okay, as we go through. So as we looked at this, it's not even, right? And if I just checked the odd side of the function, it's not going to be odd either, okay? But now let's talk about the pictorial information we have from the graph. If it's going to be even, that function's centered perfectly on the y-axis, okay? If it's going to be odd, split the function by the y-axis and rotate that axis 180 degrees with the function in it, and it should come back to itself. In this particular picture, it will not. So we've got to know, not only from our algebra check, but also from my physical geometric manipulation around the axis, that this will be neither. And does it make sense why? The way we defined an even and odd function, it doesn't fit either one of those definitions. So it's a neither. We're doing good with whether it's even, odd, or neither. Okay, now, right now, looking at this graph, I'm telling you, it's not odd. I mean, it's not even, I shouldn't say. It's not even. But we got to determine whether it's odd or not. And I didn't give it away. I was just thinking in my head. But keep in mind on this, if I rotate this, remember that flip? Ideally, it should be about my axis. Okay, I've got to kind of, it might be odd, okay, but it doesn't fit perfectly, right, as I'm looking through that. So what I want to make sure as I do this, I know how to do the algebraic check. So I take my original function, and I pop in the opposite of x, okay, and I evaluate. If all the signs changed, then it's odd. If none of the signs changed, then it's even. If parts of the signs change, then it's neither. So go for the evaluation, see what happens on this one for you. Okay, so check with your row partner, see what they said. And when we do this, we're doing two things. One, you're taking a break from listening to me, but more importantly, you are talking about this material with somebody else, hopefully using the same vernacular, the words, the jargon, what we're doing. But the other thing is you're getting more oxygen into your brain because you're talking, you're moving around. So it gives you a mental break too. All right, so take the next minute and a half, compare, go. Is it going okay?
Yeah, I think so. I get this clip and stuff.
Okay.
On the right track.
Yeah, should. It looks like the sign itself changed because this one's going to be positive, but the top sign changed. So I'm saying changing the sign overall when I do that. So now when I go through and I go through the check, this should be an odd function based on the math I'm doing. Okay, does that help? Okay, but I hate it when I give it away. But I was thinking about, it's not even. But I was like, God, is it odd? How do you know? And I was like, and I got to go over that check, the visual check. Okay, so now, is it okay? Yes or no? Are there clarification points? We feeling all right with this? Yes, sir. How come it's not neither? Let's talk about that. When I'm looking at a fraction, if I just change one sign, I've changed the sign, right? So when we're talking about neither, although this one didn't change down there, right? Overall, the function's negative. I flipped it. Okay, does that make sense? And that's why it's not neither. Most of the time, the indicators for neither is like, I'm going to make up a different function, okay? I'm just going to play. So if I'm looking at an x squared, yeah, just minus 3. X, and I put that in. If I put the opposite in here, I get out the same answer. I put the opposite in here on this 3x, I get the opposite answer. That's an example of neither in this case, but because I'm working with that fraction, it's going to be odd because of that change, because I changed the fraction sign. and it's just a single fraction. Now, I guess if it were to be something other, like a neither, the original would probably have to be like +4. Now, what happened is, as I do that, if I make that change, this sign won't change now. Because although I put in the opposite of x in these points, this won't make the change, so I'll be sitting here like this, and when I take the opposite of it all, and I'll go, oh, okay, the opposite would make the change here if I decided to do that. But because when I put in the opposite of x, the change didn't happen, it's not going to be. But that's an example of a neither in this particular case. And keep in mind what it is. This isn't an even function, and with that adding 4, I slid it up 4 units on the graph. Okay, so then I took away my point symmetry point. Okay, by adding that 4, so no longer is there point symmetry around the origin. Okay, does that make sense as I'm going? Because it won't come back to itself. So that's why it made it, that's why that one move would make it a neither. We're gonna get rid of those because I'm gonna forget that, and people are gonna go, Bloom, what are you doing? That's completely wrong. It's like, yeah, you know, you're right. Okay, are you okay with that? Now, what I'd like you to do is do one more. For time, I want to get through notes today, but we're going to come back to these to practice because guess what? It's on the test. Okay, so I want you to practice A and D, whether they're even or odd. Okay, so just go ahead and look through it and apply the rule as you go. You might even be able to tell, but you got to show, verify with algebra. And I also want you to see it graphically. So go ahead, grab your calculator and check out what it looks like. Now, there are limitations with your windows in your graphing calculator, okay? Because you may or may not be able to see the whole thing the whole time, so that makes it tougher. There are other things we can do to check in order to help us come to a conclusion that we have a sneaky suspicion on, but to mathematically check it so we can be more comfortable with our conclusions. And we'll get to those. Okay, we'll be talking about limits and what happens to the function as it tails off to infinity. Okay, now we've had the opportunity to do our work, and unfortunately for those people at home, you guys are seeing this for the first time. The folks in class are seeing it for like their 8th take, because I keep forgetting to start this thing. So here's the deal. When you pop this in and you have a constant in the function, if you have positive even exponents, okay, if you have even exponents, you have a really good chance of having no sign changes, okay? So if I'm looking at this from the original function to my changed, the signs are the same, the function's the same. We're thinking it's an even function as we go. And now the even function rule is opposite of x is equal to f of x as I go through. So it should be an even function. Okay, and we check that algebraically. But now if we're looking at this other function, as I pop in the opposite of t in for t, and I'm looking at the fact that things are going to change all the way through because I have no constants. Okay, if I have a constant and I'm considering an odd function, it's not going to happen because the constant won't let the signs change. Okay, so as I'm looking at this, my signs changed completely in the function. So keeping in mind, if I took the opposite of the original function, my signs changed completely. This is the same. So I'm just doing that to make sure that you recognize the odd function as we go, and that's where we're going there. We have other things to practice, and because of time, I'm not doing it today, but I'm going to encourage you to look at it on Monday because we're going to practice this again. Okay. Going over on the other side, just kind of a breakdown of what we did. If none of the signs change, the function should be even. If all of the signs change, the function should be odd. Now, if there's a partial change of signs, it should be neither. And I want you to keep in mind, I can combine these in quotients. I can put an even function over an even function, an odd function over an odd function, okay? And I don't even have to have them even and odd. They could be neither and neither. And what's the relationship? Okay. So as I'm looking at an even over an even, that should be an even function. If I have an even over an odd or an odd over an even, I should come out as an odd function. And then if I'm looking at an odd divided by an odd, I should be able to come out as an even function. And then neither over whatever or whatever over neither, just going to give me a neither function. And remember, it's all about where it's located on the axis. An even function has the y-axis splitting the function evenly in half, okay? It's like I folded the paper and it came back on itself. An odd function sitting on the xy coordinate axis appears as if I've rotated it about the origin 180 degrees, and that's called point symmetry, okay? And something you did in geometry, it's a 180-degree rotation about the center, all right? Now, asymptotes. We've talked about them, okay? Can we identify them? I've got some in here, but I want to talk about different asymptotes that we've got going on. Now, in this particular function, if I factor this, I've got 2x squared all over 2 minus x times the quantity 2 plus x. So right now, I know I have a vertical asymptote at 2 and 1 at negative 2. Okay? Now, I can talk about my verticals as I'm going through. Now, my horizontal asymptote is about limits. And you guys worked with limits. Well, you didn't work with limits last year. They gave you like 5 rules last year. And the rules were about whether it had a horizontal asymptote or not. Okay? Well, here's the thing. I will know something has a horizontal asymptote if it converges on a value as my value of x gets bigger. And what that means is x approaches infinity or if x approaches negative infinity, okay, and I have the original function in my argument. If I think about really big numbers, the thing that's going to take over is my x squared. Although I'm multiplying it by 2, I've got 2 over negative x, okay? The 4 is in there, right? But when I'm talking about monstrously big numbers, if I'm a billionaire and someone goes, here, Bloom, here has 4 cents. I was like, ooh, cool. That'll really change my fortune. Really? Would it? I mean, 4 cents? When I'm talking about a really big numbers, the 4 drops away. I want you to be thinking about that. And I want you to think about the effect that I take a really large number and square them. Since the squares are the same, what's x squared divided by x squared? We got 1, right? So really what's affecting this function is 2 and the negative with the x squared. So this is going to approach negative 2. Okay? That is my horizontal asymptote. Okay? It's approaching a value. When both variables, the numerator and denominator variables, are the same, the constants take over, okay, and tell me what they approach. Now, as I approach negative infinity, because it's a negative and both of them are squared, that negative in the negative infinity is taken out. So this second function, will also approach negative 2. That's how I know I have an HA of y equal negative 2. I have my VA, x equal negative 2, and my other one of x equal 2. Does it make sense how an HA was arrived at? Have you seen limit notation before? Okay, some people have. Here's the deal. I don't want you to be scared away. They will use it next year. What it really is communicating to us is there's a limit, okay? There's a value that it's going to be the ceiling, okay? Or not. We're checking to see about a horizontal asymptote. As I approach the largest number I could imagine, okay, there's always another number bigger. So when we're talking about it's approaching positive infinity and negative infinity, we're talking about incredibly large numbers. So I want you to think about the behavior of the function when I have an incredibly large number in it. Will it approach a particular value or will it diverge to infinity? is it can converge to a value or diverge to infinity. If it diverges to infinity, there's no horizontal asymptote. If it converges to a particular number, then we have a horizontal asymptote. Okay, and it really comes down to horizontal asymptotes has that one rule about divergence and convergence. Okay, last year you had like 5 different things. Well, if it does this, if it does this, if it does this, don't need that anymore. Okay, you can throw those things out the wall, out at the wall and out the window. Okay, but vertical asymptote come from non-removable points of discontinuity. We talked about that yesterday, 2 days ago. Vertical asymptotes. Okay, maybe yesterday. It seems like it was 2 days ago. And then we have horizontal asymptotes. Those were the rules we were shown last year. I don't use those rules. I just use what's the result in the limit as x approaches infinity and negative infinity with the function being considered. That way I don't have to memorize rules. I actually have an understanding of the restrictions that are going to happen with the function as I think about it approaching a really incredibly large number. New things. Okay, so we're going on. Here's the definition of horizontal and vertical asymptotes. The line y equals b is a horizontal asymptote of the graph of a function y equals f of x if f of x approaches a limit of b as x approaches the positive or negative infinity. Okay, so in limit notation, that's what it means. This is about the horizontal, and it's exactly how I found the horizontal asymptote on the previous problem. Okay, and it follows the rules that we have laid out for horizontal asymptotes that you learned as Algebra 2 students. Okay, I'm gonna be honest, remembering the horizontal asymptote thing is gobbledygook if you can understand the limit idea. Okay, if it's going to converge to a value, that's where your horizontal asymptote is. If it's going to diverge to infinity or negative infinity, you don't have one. Okay, I mean that really comes down to the rules as we go through it. All right, now vertical asymptotes. Hey, if it's a removable discontinuity, okay, hey, or if it's just a non-continuous discontinuity when we're going through it, that's what we're looking at. Now we're going to identify the asymptotes of this graph algebraically, but somebody did them already, so we're just going to get rid of this, and I'm going to have you guys find them as we go. I just wiped out everything out. So what I want you to do is find the asymptotes, horizontal and vertical. Okay. So think about what's going on. Do the horizontal first. Those are the ones you're most comfortable with. So show how you find them. Show how you find them algebraically. Remember, the first one's factoring the denominator, and where those are 0, those will be your vertical asymptotes. So my first thing, I've got x squared minus x minus 2. So I got x minus 2 and x plus 1, just looking at it. So now I have my vertical asymptotes at positive 2 and negative 1. These are already drawn on the graph, but that's how those were arrived at. Okay. A couple other things about the graph. Quickest, fastest point to find on a graph, put 0 in. Okay. You can find where the y is real quick on this one, right? Do you see that at x equals 0, y is 0? So you actually have the origin taken care of. So I need you to get in that practice. Okay, I know where the asymptote is. I know where the graph is 0. Okay. Now, the next thing. What's my vertical asymptote? Got them. Horizontal asymptote. I've got, this is a bigger power than this one. So x over x squared is what I'm going to consider. What will it converge to as I square an incredibly large number? If I have a billion, but I have a billion squared, it should converge to 0. Are you okay with that? Okay. And according to the rules that we just wrote down, since the power of the numerator is less than the power of the denominator, the largest power, it should converge to 0. Okay, as we're going through there. So I got my horizontal asymptote. That's what I'm looking at with my, that should be a 0 for both of them as I'm going down to it. That's how I use the limits. I just reasoned from the limits with the rules you learned last year. And I'm telling you, the limit thing is a little faster. I don't have to remember all the little pieces. But those pieces that I do tell you is a result for understanding how the limit works. Okay. Now, I have my vertical asymptotes, my VA, is where x is equal to 2 and x is equal to -1. And you'll see that that's where those are. It's x equal 2 and x equal -1. Can't say it and write it at the same time, apparently. Okay. And then I've got y equals 0. So I've got this puppy going across at 0. Now, you can't cross your vertical asymptotes, but you can cross a horizontal. Horizontal asymptotes are crossed at times, one time. I've never seen them, at least the ones that we work with, cross more than that. Okay. I would defer to my limitations of, I have not seen all the possible graphs in the world that are possible. Okay. So right now, I just know for sure that they cross once. Okay. Now, do you have a, I don't know, a feeling on whether this graph's even or odd? Could it be odd? We'd have to check it. Could be odd. Looks like it could be odd. You know, if I take the opposite, but I've got some signs that are going to stink around, but it's just not slightly, it's neither. Okay, as we're going through. But right now, identify the horizontal and vertical asymptotes. That's what we did. Are you okay and comfortable with that? Okay. Oh, I got some end behavior stuff. Let's check that out. End behavior. Okay, so our end behavior is our horizontal asymptote gives us one kind of end behavior for a function because it shows how the function behaves as it goes off towards the end. Okay, and it says, does it tend to some point? Because remember the horizontal asymptote in some part of the function, if we have one, our function gets really close to it as it tails off to infinity and negative infinity. Okay, now parts of the function could go and have a range that goes beyond that, and we saw that in our last function. But the behavior, the end behavior thing, is what's happening on the outside of the function, okay, as we're going. Not all graphs approach lines, but it is helpful to consider what does happen out there. We illustrate with a few examples, okay? Now, match the function with the graphs in figure 1.35. I've got graphs down here. By considering the end behavior. As your values approach negative infinity and positive infinity, what's the behavior of your graph? Okay, and try to do it sans calculator without it. Okay, so what happens to the denominator as x squared plus 1 as x gets very large? That's really what you're considering. So as you're looking at these, consider which one of these graphs go with A, B, C, or D. I'm going to give you about 5 minutes. I think we have about 8 minutes, so I'll have 3 minutes to explain myself. Okay? Remember, find your horizontal limit, find your vertical asymptote, if there is one. Look at the powers of the graph. Consider what's going on. Okay. So as I'm doing this, I'm looking at the limits. Okay. So in the second one, I've got limits as well. And the third ones, I'm looking at limits. And the fourth ones, I'm looking at limits. So that's the first thing I did. I'm looking at the limits. In the first one, in A, it's approaching 0. Which of the graph have the end behavior as I go further out from the origin, left or right, does it approach 0? Are you okay with graph number 4? Graph number 4, based just on end behavior, sneaky suspicions, just based on end behavior, okay? Based on end behavior, I'm thinking graph A and graph 4 go together. Okay, HA is 0 if I go through, so I'm looking at graph 4. Are you okay with what I did? And I just started my suspicion with end behavior in the graphs. Now, in the next one, I'm looking at it approaching 3. Which one of the graphs that I have left over seems to approach 3? Ideas? I'm taking a willing participant to throw out a number, or in this case, a Roman numeral. Yeah, you want to go out on a limb? 3. Isn't it fun that Bloom put the 1 for 3 on the third graph? No. I wish I had done that because I would have. Okay, we're talking about graph number 3. Okay, because it's approaching as it goes to 0, the value of 3. Okay, now my limit here in C, it approaches negative infinity and positive infinity. So it's not approaching anything, it diverges to negative infinity and positive infinity. Which one of the graphs that are left do both? Or it could be that way too, but they're doing both. It's going to positive infinity and going down to negative infinity. Do you see graph 2? Okay, and it was just on end behavior. I didn't get fancy. I didn't pull up any points. I just considered what happens to the graph as the graph keeps going on to infinity. Okay, my last one, people, well, that's the last one, Bloom, you don't have a choice. Let's double check. Both values, when I consider the limits as x approaches infinity and negative infinity, tend to positive infinity. Well, whoop, it's like a stick up, right? It's going up, it goes all the way up, it's graph 1. Okay, now I'm hoping that that makes sense today as we're going through things. Please make sure if you've got questions, you ask. I'll do my best with explaining it as we go. Okay, thanks for your time today, you guys. And I'm not sure if this is the new assignment. This is the assignment I've been following, this new change. Those are the assignments I've been following, not the other stuff. So you guys have seen this through your sheets. This plus extra worksheet, I'm not going to be too sweating right now. I just want you to get these, and we'll talk about those extra worksheets on Monday. Okay? Now, aside from that, make sure you're doing those piecewise graphs on 32 and 33 in your notes. Okay, I want you to practice. We're going to talk about those right away on Monday. Okay, we're going to correct those in class because I know people are like, oh, but this is all on Schoology. This is the stuff that I've been working on Schoology.